Hi, welcome to my channel. After a hiatus of a few months, I am back. The next series of lectures is going to be product topology. That is going to be, we are going to deal with arbitrary product, that is product of arbitrary collection of topological spaces. The culmination point will be the much dreaded Tychonoff theorem, which says with the product topology, the product of compact spaces is compact. And this, many people have difficulty even if when they go through my articles and read, and even in MTTS sometimes the teachers try to give a proof, they get stuck or they miss certain points. The reason I always found was that they don't spend enough time in reviewing arbitrary products, looking at some very trivial examples, okay, so that you become very comfortable with the notation, okay. And one rushes through those things and quickly get into the Tychonoff theorem, because always people have a penchant to go to the deep theorems first, okay. But if you are not comfortable with the notation, then you get lost. That's what happens with many people. So my request is, even if you believe that you know Cartesian product, please spend some time and bear with me, get to the notation. And I'm also introducing a new notation which is not in books, so it makes very compact, so that life compact, okay, pun intended, life much easier, okay. Please bear with me. Let us go back. Yeah, so you can download the list of my videos on my channel using this. Let me see whether I have screen shared. Yes. And okay, you can also go here and try to get the articles which are mentioned in my channel in this place, okay. So the references are few of my articles. One is an outline of topology course, the other one is generating topologies, O is missing, and the third is Tychonoff's theorem. All these things can be downloaded from this article. And another thing is, there is a forthcoming book, a topology, a core course, which is co-authored by one of my former students, Vikram Maithal, and myself, okay. Right, so let us get to that. So as I said, the first thing is that we want to talk about review of arbitrary products. Arbitrary product, what does it mean? Okay, so let us go through. It will take some time for me to get used to the graphics board. Even otherwise, you know, my handwriting is not that good. Now I have been out of touch, so you have to bear with me. Suppose xi are sets, I is an indexing set. We will assume I is not 5. These are just sets. Then we want to define what is meant by Cartesian product xi over I. This is the notation. Hey, remember, I could be anything. Need not be 1 to 3 or 1 to n or I natural numbers. It could be any arbitrary thing. Okay. Now how do I define? It is by definition set of functions x from the indexing set to I to xi, so that x at I, okay, this is a function, right? It takes values over I, okay, it takes value in xi. Do you understand this? This is the first thing you have to understand, okay, from I to this. We will look at some examples, don't worry, okay. So at I, it has to be in one of the elements in the union, but I don't want to be xi should be an element of xj. I want it to be an element of xi. This should be true for all I. Okay, this is what we mean by Cartesian product. Okay, that this is non-empty is usually axiom of choice. If xi are all non-empty and I is non-empty, then this is non-empty. Okay, let's not worry about such a logic problem. Let logicians work look at such things, but we want to understand how to deal with product xi. Okay, right. The first thing I would like you to do is how to imagine. Okay, the way I would imagine will be something like this. I will think of this as I, and each xi will be like this. This is my, it's I, and this is my xi, capital Xi, and this will be my j, this will be my capital Xj. This is what I do. Okay, therefore what will be my, so at I, my xi should lie here and xj should lie here. Okay, and as usual, like in sequences, we will denote xi by the value of the function x at j, sorry, x at I. Okay, right. So let us look at simple example. Suppose x equal to 1 to n. Then what does it mean? So my product xi I equal to 1 to n is by definition set of all functions x from 1 to n to union xi, so that for each I, x at I must be in xi, right? So this is the definition, right? But you may remember in your basic set theory you will define x1 cross x2 cross xn to be the set of ordered n tuples x1, x2, xn, so that xi belong to capital Xi, right? This is what you call Cartesian product. Okay, this also we call as Cartesian product. This is called the Cartesian product. Product of xi. Okay, now these are not the same. Okay, if you are a purist, these are not the same. Because it says this just set of all functions from 1 to n, so that x at 1 takes in value in capital X1, x at n takes the value at x at n. That's all. Okay, there is nothing like order. But what we do is we set up an obvious bijection phi, that is phi of x. I can write it as x at 1 comma x at n. This is x1 cross x2 cross xn. So what I want to say is, when we define like this, there is no order. You understand that? There is nothing like the first factor is x1, second factor is x2, or nth factor is xn. There is nothing like that. It's just something. It's of all functions. Okay. The only way I can recognize an element of x here is to tell you what is the value at I. Okay, where I is 1 to n. That's all I know. Here, these are ordered n tuples because there is an order. Okay. Now, this is very easy to see. This phi is a bijection. Okay, so pause, review, proceed. See, these are the things people don't take time to explain carefully. Okay, so you do not know how to work with Cartesian product as we define here. Okay, because we know how to define Cartesian product x and y. X cross y will be set of ordered pairs x comma y, blah blah blah. But here it is not. It's something else. So one has to learn to work with that. Okay. And similarly, if I equal to n, okay, then my Cartesian product, okay, let me write it x xn n and set that xn. Okay, for each n I have given s at xn, which is non-empty. Okay, this set of all functions x from natural number to union xn. You understand that? So that x at n belong to xn. This is our definition. You see that how many times I keep repeating? Just because of the definition, people jump. Don't do that. We are slowly getting used to how to work with Cartesian product in the abstract way. Okay, take some time, right? But I can also define as an infinite tuple. Here, what are the elements? Any element is of the form x1, x2, xn dot dot dot. This is a ordered infinite tuple. Okay, right? Now again there is a bijection phi. Okay, what is that? Phi of x is going to be x at 1, x at 2, x at n and so on. Okay, this is a bijection. So what I am trying to say? I am trying to say if I equal to 1 to n or I equal to capital N, Okay, then this one I in I, okay, I in I can be thought of as x1 cross xn, or okay, let me call it in n in n, and xn can be thought of as x1 cross x2 cross xn dot. Any element here, instead of thinking of a function, I can think of as an n tuple, ordered n tuple, or in the second case, instead of a function from natural numbers to union of xn, I can think of it as a ordered infinite tuple x1 x2 xn, so that the nth coordinate xn lies in the space set xn. Okay, please spend some time, pause, review, proceed. Okay, now let's look at a very concrete example. Suppose I equal to 1 to n, right, and my all x I equal to x, a fixed set. Fixed, of course, non-empty. Okay, then what is product? I in I of xi. This is nothing other than x cross x n times. When I say equality, with understanding, that is, this is set of all functions. This is set of all function x from 1 to n to x. That's it. Because what is union xi? I equal to 1 to n. That is just x itself, right? Therefore, this is, and what is the bijection I have? This x goes to x at 1, x at n. That is ordered n tuple x1, x2, xn, so that each xi is that. This is what we call x power n. Like when x equal to r, you call it r power n. So I can call it x power n. Do you understand this? Yeah. So these are the small things. Okay, be very comfortable. Don't say that they are very easy. Go ahead. Okay, then later when we want to use, you will get stuck. Okay, we will go back and forth with ways of identifying the product space as an ordered n tuple or infinite tuple or something. Then you will get confused. So spend some time. So next is, let's suppose I equal to n and my xn equal to x for every n. Then what do you think my product xn and n in n? This is nothing other than, when I say nothing other than, set of all sequences in n. Do you understand this? Yes. Why? Because if you give me x in the product n in n of xn, this is what? This is a set of functions from natural number to union xn, but that is nothing other than x. Therefore, what do you call this? This is a sequence in n. You understand that? That's the definition. So therefore the infinite tuple, this I will write as x equal to x1, xn, etc., where xn is x at n. Yeah. So take some time, review this. These are all very easy. Okay. The next example we will slightly make it little more difficult. Okay. Now suppose my I equal to t at r. Okay. Okay, I equal to, let us say, s at x. Okay, maybe you call it a. Okay, yeah, I equal to a non-empty set a, and my xi equal to r for all I. Let me call xa equal to r for all a in a. Okay, this is the third example. Do you understand this? I am sorry for the notation. The indexing set is a non-empty set a, and for each I in a, that is I is equal to a, therefore I call it for every a in a, then I have a non-empty set xa, right? And what is that set? That is nothing other than r. Then what is product xa a in a? Again go back to the definition. This is nothing other than set of all functions from a to union xa a in a, but that's nothing other than r. Therefore this is nothing other than set of functions real valued functions on A to R, which is same as set of real valued functions on R. Yeah, again pause, review. These are all very easy. If you want to be very comfortable with the arbitrary product, go through these examples. Okay, you can see how we are shifting the ideas. Okay, very good. Now let us try to see how to visualize them. Okay, suppose my I equal to 1 to n. Then how will I do? I will think of this as 1. I'll just give a different colors so that we will be see. This is 1, 2, and this is my n. Then what will I do? I'll think of this is my x1, and this is my x2, this is my xn. And how does an element x look like? Element and product. Okay, I equal to 1 to n of xi. That will look like some element like this. Something in x1, something in x2, something in xn. That's it. Okay, this is a visual representation. Don't think of the x-axis, y-axis, etc. This is just a thing. Okay, right. Now suppose, let us say, look at another example. Suppose my I equal to n. Okay, then how will I think of this? It's the same thing again. Now I'll keep going. Okay, so this is going to be my 1, 2, 1, 2, n plus 1, 1, 2, etc. Then what will be my thing? The space will be x1 will be this, x2 will be this, xn will be this, xn plus 1 will be this. And how will a point x will look like? X belong to xn, n. That will be some point like this. Something x1, x2, xn, xn. That's it. Yeah. And let's look at a third example. My I equal to, let us say r, and for every t in r, my xt is also r. So from whatever I said, do you remember? My product xt t in r is nothing other than set of functions from r to r. Remember, there I took this to be a, and for each a I took xa to be r. Let us look at the last example. Instead of a, I am taking r. Therefore, set of functions from r to r. Do you understand that? Okay. Then set of functions from r to r. How do I do that? Again, the same trick. What do? I take my, okay, this is my, okay, I set, which is r, and for each t I am going to have, this is my t, this is my xt. Okay, and this will be my xs. And so on. So how will an element look like? It is going to be a function. So if you keep on drawing like this, I will just draw a few more. Okay, so that's going to be an element is going to be like that. Sorry, color, I would like to keep the same color. Okay, these are my x. You follow that? This is my typical x. This is x, and this is xt, x at t, this is x at s. Yeah, just to make sure we understand, let us look at an example. Suppose my I is going to be r plus. maybe you take, if you want, 0 to infinity, okay, greater than or equal to 0, okay, and my xt for t in I is going to be 0 to t, right? Are you following? So how will I visualize? Again the picture is the same. So this is my 0 to infinity, okay, and this is my y equal to x line. Do you understand that? Therefore each t, let me write a t, for each t my xt is this, that's it, and for each t my xt is this, right? And what is x0? It is singleton 0, right? Are you following? Now I will give a thing. Suppose I let me define a function, okay, an element x from I to u r, like that, x of t equal to t squared. You understand that? So I want to know whether x belong to product t in I of xt. Okay, this is an arbitrarily cooked function. Do not get confused. This is just want to make sure how to work with Cartesian product. That's why. Okay. Typically speaking, what is the you cannot ask this kind of thing. If x is from I to r is a function, whether if you think of it as a function, does this function belong to the Cartesian product? You understand this? So question is, does it belong to this? Okay. What is the answer? Answer is no. Because for example, when I take t equal to 2, what is x? X at 2, that is 4, but what is my x2? X2 is 0 to 2, right? Therefore x at 2 does not lie in x2. Therefore my x is not an element of product xt, t is in I. Okay, pause, review, proceed. Okay, right. So these are the example. Please go through it again. Okay, I gave enough examples. Now let's go to the next step. The next step is, so let us assume I is an indexing set and I have product xi, I in I, right? What we want to do is various things. So if an element x belong to, remember what is that x? Keep on writing, okay, so that you will become comfortable. That is such that for all I, x at I belong to xi. Okay, we will denote x by xi like the way we do sequence, where xi is x at I. For example, I equal to n, then this will be the sequence x at n, xn, right? Xn will be x at n. So I will write it as x1, x2, xn, right? So in view of that, we will simply write xi, I in I if you want, but I will not write. It's understood. Are you following me? Any element x in the Cartesian product, we will write as though as an infinite, okay, tuple of some kind. Okay, don't call it, it's just a notation. This actually stands for this function. But in the case I equal to n, it is nothing other than ordered infinity and tuple, ordered infinite tuple. Are you following? Make sure you understand this. Okay, this I, we call it the ith coordinate of x. What does it mean? This is nothing other than the value of the function x at I. But we will call it ith coordinate because we will call it the nth term of the sequence, right? So in similar fashion, we will call it the ith coordinate. Is that okay? Now therefore, I have a map pi I from product xi, I in I, to the set xi. These are all sets. Do you remember? This, how do I define? Pi I of x is nothing other than the xi. That is nothing other than x at I. Okay, this is called the ith projection. Are you following? Yeah. So I have a map For each I have a map. This is the projection maps. Okay. Now the question I want to understand, this is going to be very crucial for what we want to do. Okay, is the following. Let vi, or that is a ui, be a subset of xi. Okay, it may be empty, non-empty, I don't care. Okay, a subset. Okay, then I want to know, remember, if whenever f is a function from x to y and b is a subset of y, I have what is meant by inverse image of this. This set of all x in capital X, so that fx is in b. Do you see that? All of you should be very thorough, but every time I repeat. Okay, this is how you master. So simply don't assume I know that. Always repeat so that you will become comfortable. When you want, you can use it. So I want to know, so therefore pi I is a map from product xi. I will not write I in I hereafter. That is understood, to xi, and ui is a subset here. Therefore I can ask, what is pi I inverse of ui? That what is this? This is going to be a subset of this set, right? So I want to know what is the subset. Okay, I will do the abstract case first, then we will specialize to concrete cases. Okay, so when does x belong to this? X belong to this. If you remember that, when does x belong to f inverse of b? If and only if fx belong to b. This is a Tarak mantra to deal with inverse images. Okay, therefore this is if and only if pi I of x belong to pi I inverse of ui, if and only if pi I of x belong to ui. But what is pi I of x? That is if and only if x at I, that is xi, belong to ui. Okay, and remember, I is not varying, it's a fixed set, there is only one. Therefore when you give me x, an arbitrary element in product xi, I in I want to know whether pi I of x belong to ui. Okay, sorry, whether x belong to pi I inverse of ui. There is only one condition. What is that condition? If you think of this x equal to xi, let me put it as a j now. Okay, x belong to pi j inverse of uj. Okay, I in I. Okay, right? If and only if there is only one condition. Now look at the jth coordinate xj, that should be in uj. Are you following? I am sorry if I just all of a sudden changed I, but you understand the reason. I want to write x as the infinite tuple xi. Then when does x belong to? Okay, sorry, this belong to pi j inverse of uj, if and only if there is only one condition. You can ignore everything. Okay, look at only that particular element. For example, okay, right? Are you following? Right. So for example, let us look at a simple case. Suppose my I equal to n. Okay, my, let us say, xn equal to r. Okay, and let me fix, okay, un equal to, let us say, n to 2n. Right. Now let us look at an x in product n in capital N of xn. Right. I want to know when, okay, x belong to pi n inverse of un. What does it say? If you write x, remember I can write as n tuple. Okay, right? So when does that belong to that? It says, look at xn. This xn should be an element of n and 2n. For example, when equal to 2, my x2 should lie between 2 and 4. Therefore, if I give an element something like 1, okay, 4, 5, so let's say 5, minus 1, 2, etc. I want to know whether it is in pi 2 inverse of u2. It does not. I only have to look at the second element. The second element is 5. x2 is 5. Does it belong to 2 to 4? No. So it is not. Right? So let us consolidate what we did. Therefore, pi j inverse of uj is set of all x in product xi, so that xj belong to uj. That's it. There is only one condition. That means if you somehow think of this, this is nothing else than product of, okay, ui I in I, where ui equal to xi for I not equal to j, and uj is uj. Maybe you write it as bi, and vj is uj. Are you following? In other words, these are all full spaces. At the jth place, only this will be there. This is my uj, and all other places it will be whatever you want. This is x1, xj, this is xi. Okay, when it comes to this, it has to be only this. So all the elements can be anything which comes, but when it comes, it has to go through this. Anything, but when it comes to jth place, it has to lie in here. Try to visualize these kind of things. You will never see in books, etc. Even in my book, I can only give some little bit examples. Okay, pause, review, proceed. So the first thing you should think of this is, again think, let me repeat, when x belong to this, okay, there is only one condition. What is the condition? The jth coordinate xa should be in uj. That's it, nothing more. What do I know about other xi? They could be arbitrary elements. If I is not equal to j, xi could be any arbitrary element of capital Xi. But when I equal to j, then xi should lie always in uj. Okay, please understand. So let us look at a concrete example. Suppose my I equal to 1 and 2. Okay, my xi equal to r. Right? You understand that? Okay. Now let me say on x1, let me take as something like -1 to +1. Okay. Now how will I visualize x1 and x2? Therefore my product I equal to 1 to 2 of xi, which is nothing other than r cross r. Again, when I say r cross r, we can identify with ordered, okay, pairs, right? This is only functions. Remember again, see, these are the things you should be able to shift your mind. When I say x belong to this, it means it's a function from 1 to 2 to r. That's all I know. But it says I can identify with the ordered pairs of r cross r. Therefore, how will it look like? So this is -1 to +1. Maybe let us make it -2. Okay, this is -2. This is +1. Therefore, my set is going to be this. Okay, this is pi 1 inverse of, okay, let me continue, not x1, u1. u1 is contained in x1. Pi inverse of u1 is this ordered in tuple. And when I take u2 to be, let us say, 0 to 1, then pi 2 inverse of 0 to pi 2 inverse of u2 will be the same picture I will do, that will be 0 to 1, right? So this is 0 to 1. Okay, so when does an x belong to this? Let us think of this x1, x2. When does it belong to this? If only if x2 lies between 0 and 2. And here, when does it belong to this? If only if x1, x2 belong to this pi 1 inverse of u1, if only if x1 lies in between -2 to 1. Are you following? Now, when does x1, x2 belong to pi 1 inverse of u1 intersection pi 2 inverse of u2? If it belong to this, this means x1 must lie between -2 and 1, and here it says x2 should lie between 0 and 1. Therefore, this is nothing other than -2 to 1 cross 0 to 1. That is this common area. Yeah? Okay. Now I will introduce the product topology and stop there. So what is the product topology? if you had gone through even finite product, I emphasized not the standard way of writing product topology. I motivated how to look at it. So we are going to do the same thing. So for I is an indexing set and xi's are now assume topological spaces. Then we make a product xi. This is just a Cartesian product. This is a product set. Now topology, right? Now we had already defined the maps I and I to xi. Okay, this is for all I. So what I want is fix an I want a topology on this set so that this natural map becomes continuous. Please review my product topology, finite product. Okay. If you only thought of u1 cross u2 kind of thing, then you will miss the point. Okay, are you following? So what I want is for each I want this. Okay, we look for a topology tau, let us call tau p on the set product xi such that for all I the projection map phi I from product xi to xi is continuous. Are you following? So these are all spaces. How many spaces I have? As many spaces as number of elements in I. Right? Now all these maps should be continuous simultaneously. Not only that, I can always take the discrete topology on the product set. Cartesian product xi, I can take the discrete topology, it will make continuous. So what is the question I should ask? I should look for the smallest topology. So look for the smallest topology which makes this thing continuous. So product topology on the product xi and I, okay, by definition we do not know whether it exists. Smallest topology on the set product xi said that each projection map phi I is from, let me call the smallest topology tau p, such that product xi and the topology to the topological space xi tau I, okay, this projection maps become continuous for each I. Why does it exist? We already know there is a discrete topology which makes the product on the product set, which makes each of the phi I continuous. Therefore, the set of topologies such that which makes each phi I continuous is non-empty. Intersection of topologies will be a topology, and that will be by definition smallest topology. Again, okay, look at my video on generating topologies. Okay, look at that. Okay, so this is what we want. Okay, so the important point I want to look at is, therefore, suppose there exists. Okay, suppose tau p exists. We know it exists. Okay, now suppose I have a ui which is an open set in tau I. Okay, that is ui is an open set in xi, right? Then what do I know? Since each phi I is continuous, phi I inverse of ui, okay, that must be in tau of p, right? So whatever I you take, whatever ui you take, then phi I inverse of ui must be in tau p, right? You understand that? Yeah. So I can look for the smallest topology tau which contains all these elements phi I inverse of ui, as ui varies over tau I and I also varies over I. Okay, we know how to write down explicitly the smallest topology which contains all these elements. Okay, and please look at my earlier videos. Okay, in the next video I will review this and I will prove it's the smallest smallest topology which makes all these functions continuous. Okay, tomorrow we will prove that. Okay, in the next lecture. but please review. Okay, pure. So please go through this whatever I did. Okay, as I said, many people struggle with product topology and my proof of Tychonoff's theorem because they believe that they know Cartesian product, they just like that go, then they run into problem. Okay, please go through this, take your time, review it. Once you review it, after that you will see it's very easy. Okay, right, I have given you a warning, it's up to you to listen. Okay, we will meet again. Take care, stay safe.